Hello, it's a pleasure to welcome Oleg Lisovyi. Sorry about that. He's going to talk on Painlevé functions from Widom determinant.
Okay, thank you very much. Also, I would like to thank the organizers of this meeting and of the whole semester at the Newton Institute for their efforts to keep this alive. I would also like to ask the audience, so please feel free to interrupt me at any point and ask questions. Another option is to write your questions in the chat. So if I am able to see them, I will try to answer. Fine. So the title is Painlevé functions from Widom's determinant. So Harold Widom, who well, sadly passed away in January this year, is of course very famous in our community for Tracy-Widom distribution. So this Tracy-Widom distribution gives the distribution function of the largest value of the largest eigenvalue of a random Hermitian matrix, and we have two characterization of this of the corresponding cumulative distribution function. One is in terms of this Fredholm determinant of the integrable Airy kernel, and the second one, the second characterization, is in terms of a tau function of a particular Painlevé-2 equation, the homogeneous Painlevé-2 equation, with special initial conditions. So this is the tau function which corresponds to the so-called Hastings-MacLeod solution. Now, both Fredholm determinants and Painlevé tau functions are central subjects of my talk. However, in the talk, I will use another construction, which is again due to Widom, which was introduced by him in the mid-70s. So this construction appears in the asymptotic analysis of the so-called block Toeplitz determinants. The starting point is this. So we start from a function on a unit circle with values in n by n matrices. So this matrix should be invertible, and we place ourselves in the simplest possible situation where this matrix valued function g of z is smooth on the circle, and we will also assume it to be analytic in a neighborhood of the circle. Under such circumstances, we can expand this function into Laurent series in a certain annulus containing the circle. So this G case will denote the coefficients of Laurent series, which are certain n by n matrices. There will be two more conditions that the matrix J of Z has to satisfy. One condition is not very bounding. This is just a kind of normalization. So we normalize the determinant of J of Z so that this equality holds true. And more importantly, we assume that the determinant of J of Z has zero winding. So, for example, J of Z, which looks like 1 over Z, doesn't work. Okay, so we want the argument of the determinant of J to come back to its initial value when we are going once around the circle. Now, starting from the Fourier coefficients of this Laurent series coefficients of this matrix J of Z, we built a block Toeplitz matrix. So this is what is denoted TK of J here. So you see on the main diagonal we have G naught. On the next two main diagonal we have J minus ones. Here we have J ones and so on. So the elements, the matrices on the diagonals are all the same. But remember that all of these individual coefficients are actually n by n matrices in our setting. And the result of the first result of Widom that we are going to use in the talk is this. So the limit of the determinant of such a matrix exists as k goes to infinity. And moreover, this limit is equal to this expression here, which can be seen, which can be rewritten in a slightly different form. So it is a determinant of, okay, let me explain this notation. So we suppose we have the space H, which is just the space of L2 functions on our circle tensor Cn. Now, this H has an orthogonal decomposition into H plus plus H minus, where H plus and H minus denote the functions that can be continued analytically inside and outside. So the determinant here, the subscript H plus, means that, well, so the operator that we are considering here is an operator on H plus, so the functions with only positive Fourier modes. And so what we have here is a composition of multiplication operators like J minus 1 and J, and projections of the result on H plus. And even though the individual factors like this one here or this one here, there is no sense in talking about their determinants. So these operators are not trace class. The product of the two operators is trace class. So the determinant here is well defined. Right, and to summarize this this construction, so you see that to any loop, so to any map J going from our unit circle to invertible n by n matrices, we can assign a number d of J. So it is nothing but this Fredholm determinant. So the limit of this block Toeplitz matrix. And in the case where the symbol J depends not only on the circle variable Z, but also on some parameters, then this number d of J becomes a function of all of these parameters. So later on, this function of parameters will become the tau function of Painlevé equations. So it's what is written here. So the general solutions of Painlevé 6, 5, and 3 equation are actually Widom's determinants for some specific and importantly explicit, some specific and explicit J's. So the symbols will be expressed in terms of Gauss or Whittaker or Bessel hypergeometric functions. Right, so this is about Widom determinant. Now a few words about Painlevé equations. So the most important point about Painlevé equations is that they belong to the world of linear differential equations, and more precisely, they solve inverse monodromy problem for 2x2 linear systems. To explain what I have in mind for non-experts, let me just start with an example. So my example is this Fuchsian system having 3 regular singular points located at 0, 1, and infinity on the Riemann sphere. The matrices A0 and A1 here are supposed to be traceless, 2x2, to make this things simple. And now relating to this Fuchsian system, we introduce 2 spaces. So one is the space of all possible equations of this form here. So it is the space of all triples of matrices from SL2 Lie algebra, summing up to 0 and considered up to overall conjugation, because obviously if we conjugate A's by some constant matrix, this can be absorbed by the solution phi. And there is a second space, which is the space of monodromy matrices. So we have monodromies around each of these regular singularities. So M0, M1, and M infinity, which multiply up to identity matrix. And again, we have to consider them up to overall conjugation. So computing monodromy matrices from this residue matrices A nu defines what is called the Riemann-Hilbert map, phi RH here. And what we can now ask are 2 questions. So one question is this. One question is, can we find A's, so A0, A1, A infinity in terms of M? In other words, can we reconstruct the linear equation in terms of monodromy? And the solution of this question is very easy. It is given in elementary functions. You can just make this exercise in a couple of minutes. So A0, A1, and A infinity are expressed in terms of this monodromy exponents theta k. Monodromy exponents. Now there is also a second question, which is here. So we could want to find the solution of our linear problem starting from a given monodromy, and the solution to this second question is still possible to obtain, but it is more complicated. So it is given by a 2x2 matrix, each element of which is some hypergeometric function. Okay. So now we can try to generalize these two questions in the case where the initial linear system has one more regular singularity. So suppose that we add here something like this AT divided by Z minus T. So the position of the fourth regular singularity can no longer be fixed at some given point. So this is a new this introduces a new parameter in our problem. But otherwise, we try to do exactly the same thing. So we introduce the space of Fuchsian systems with 4 regular singular points, the space of their monodromies. We fix local monodromy exponents. And it turns out, this is another exercise which is easy to do, is that the dimension of both of these spaces for fixed value of t is equal to 2. And this allows to do the isomonodromic deformation. So for any value of variable t, we can, and any given monodromy, any prescribed monodromy, we can find a Fuchsian system with that monodromy. And reconstructing this Fuchsian system from the given monodromy is equivalent to solving Painlevé-6 equation because well, the coefficient matrices of the linear system in that case, in the isomonodromic case, they will satisfy these isomonodromy equations, and in the 2x2 case, this is nothing but Painlevé-6 equation. So the monodromy exponents at the regular singularities give 4 parameters of Painlevé-6, and 2 remaining monodromy parameters corresponding to this dimension equal to 2. They correspond to integrals of motion. And well, this just repeats what I have said. So we have a Fuchsian system, we have a Riemann-Hilbert map, and what we want to do is actually to go in the other direction. Given the monodromy, we want to find A0, AT, and A1. And if we manage to do this, then we will have our general solution to Painlevé-6 equation. Now, while inverting this Riemann-Hilbert map, it actually suffices to compute any non-trivial function on the space of Fuchsian systems. One could consider many different combinations. There are different standard choices. So one could take this trace, or one could take this trace, or something else. So our choice will be the function tau of t, which is defined as, well, its logarithmic derivative should be equal to this linear combination of these 2 traces. So this is the Jimbo-Miwa-Ueno definition of what they call the isomonodromic tau function. At this point, it is absolutely unclear for non-experts where does this definition come from. It's just one possible way to introduce a coordinate on this space. But we will see in a moment why this coordinate is a good one. So far I have spoken only about Painlevé-6, but actually for the other Painlevé equations, the procedure is exactly the same. So we only have to change the linear system that we are starting with. So Painlevé-6 appears when we have 4 poles of order 1, 4 regular singularities. Now, in the Painlevé 5 case, we have 2 regular singularities and 1 double pole. For Painlevé 3, we have 2 double poles and so on and so forth. For Painlevé 1, we have just 1 triple pole at infinity, and furthermore, the coefficient of the highest polar contribution should be non-diagonalizable, which corresponds to this odd number of cusps in this picture. Fine. Are there any questions so far? Okay, so if there are no questions, I can continue. So once again, so what we want to do is to invert this Riemann-Hilbert map. We want to reconstruct let's say a Fuchsian system from its monodromy. So this can be done, first of all, asymptotically. It was done by Jimbo in 1982 for Painlevé 6. Then in the irregular cases for confluent limits of Painlevé 6, it was done essentially in all interesting cases for P1 and P2 and P3. It is the work of Kapaev, Itz, Novokshonov in the 80s. For Painlevé 5, it was done partly by Jimbo in his 82 work and partly by Andreev and Kitaev in 2000, and there was another very recent work by Shimomura. But my point here is that so asymptotic inversion of the Riemann-Hilbert map. So nowadays, by the way, by the end of 90s, we already had very powerful tools to deal with this problem. And already by the end of 90s, this toolbox essentially put Painlevé functions at the same level as hypergeometric functions in the study of global behavior. So what we are after is not the asymptotic inversion of the Riemann-Hilbert map, but exact formulas, exact representations for Painlevé functions. And here is the strategy that we are going to use to solve this problem. So first of all, we are going to convert the initial Fuchsian system with 4 regular singularities into a Riemann-Hilbert problem on a circle. So this Riemann-Hilbert problem will be characterized by a jump matrix J. And this J of Z is the same J that we had in the Widom's determinant. So in the Widom's determinant context, this was the symbol of the block Toeplitz matrix. And if you recall, so if we have such a matrix function on the circle, we can associate to it a certain Fredholm determinant. So this will be our definition of a tau function associated to every such Riemann-Hilbert problem. And it will turn out that this tau function coincides up to some simple elementary factors with the Jimbo-Miwa Ueno tau function for Painlevé 6. So Painlevé 6 J of Z will correspond to some very specific form of this symbol. So here is the general idea, the general scheme of what we are going to do. So the initial Riemann-Hilbert problem that we have to deal with is this. So we have a contour which is composed just from straight segments connecting different singular points of our Fuchsian systems. And the jump matrices on the segments are just some constant matrices encoding the monodromy. However, at every point, at every singular point, 0, t, 1, and infinity, our fundamental matrix solution phi is expected to, well, not expected, it should have this type of behavior. So we have some power like factor times a holomorphic invertible matrix in the vicinity of this point. And so to take into account this prefactor, it is convenient to replace this initial Riemann-Hilbert problem where, well, the general formulation of the Riemann-Hilbert problem I forgot to explain, but it is this. So we have a contour, and we look for a function which has a prescribed jump j on gamma. Okay, so here this function that we are looking at is just phi, the fundamental matrix solution. Okay, outside of this collection of segments. But now, in order to take into account this power-like factors characterizing Fuchsian singularities, we can just isolate the singularities inside some little but finite circles. And the jumps on these circles will be precisely such that so they will absorb these factors. So essentially, outside of the circles around 0, t, 1, and infinity, the solution of our Riemann-Hilbert problem is just phi of z, and inside the circles and outside this big circle, the solution of our Riemann-Hilbert problem is this part of the fundamental matrix solution. So in this way, we transform the initial Riemann-Hilbert problem into a Riemann-Hilbert problem on a contour which looks like this. So we have four regular singular points isolated into circles. But this is still not what we really want. What we really want is a Riemann-Hilbert problem on a single circle. So we continue. So we cancel the jump on a portion of this segment by multiplying our fundamental matrix solution by, well, some factor which is supposed to mimic a Fuchsian singularity. So this is not the only possibility which allows to cancel the jump here, but this is the simplest one. But in principle, we could take any choice of this prefactor. It is just important to have the necessary monodromy along this contour and to be able to solve two auxiliary Riemann-Hilbert problems which appear afterwards. So you see, after multiplying our fundamental matrix solution by this factor, at least at the pictorial level, what is going on is that the contour splits into two disjoint pieces, which, so for example, if you forget about this interior, so this exterior Riemann-Hilbert problem is precisely what would we get for a Fuchsian system with only three regular singular points. And this system we can solve in rank 2. So we can solve and write everything in terms of Gauss hypergeometric functions. Likewise, if you forget about this exterior part and take into account only this, only the part of contour which is inside this circle here, then we again have a Fuchsian system with 3 regular singularities at 0, t, and infinity, which is mimicked by the jump in here. So here, I suppose for simplicity that this matrix sigma characterizing the monodromy along this contour is diagonalizable, but this is not even necessary. So this is true for generic solution with 2-parameter dependence on the initial conditions. But in principle, we could do exactly the same in the case where sigma has Jordan form. And then, so what we do, I put here a more schematic version of what we had. So what we do is that inside the annulus here, we divide the solution of our Riemann-Hilbert problem by respective solutions of auxiliary problems corresponding to 3-point Fuchsian systems. So basically what is going on is that, so I take my solution which is here, and by dividing by the solution of this interior Riemann-Hilbert problem, I cancel all of the jumps inside this circle. Likewise, outside, I divide the solution of this problem here inside the annulus. I divide by the solution of the exterior Riemann-Hilbert problem, and again I cancel all of the jumps. But the price to pay is that now we get a new jump on the circle C, and this jump is written here. So this jump is nothing but the ratio of 2 by 2 matrices composed of hypergeometric functions f2, 1. So this is some, well, a little bit cumbersome, but still explicit jump matrix expressed in terms of hypergeometric functions. So now we have what we want. We have a Riemann-Hilbert problem on a circle with a certain jump. So we can consider Widom's determinant associated to this jump. Okay. So this is a rewrite of the formula for the Widom's determinant that I had before. And here we have yet another rewrite, which makes this expression looking more familiar, well, hopefully more familiar, because this gives rise to integral operators of integrable type. So I rewrite the Widom's determinant tau of J as a determinant on the whole of H, so L2 S1 times C2, so both positive and negative Fourier modes. And so the entries of this block integral operator K, they have essentially this integrable form here. So psi plus for this entry, and similar formula with psi minus for this entry. So 2 hypergeometric expressions here and here. And now the third step is the identification. So we have to now show that the quantity that we have just defined indeed is related to our Painlevé equation. This is based on yet another result of Widom. So let me call this Widom's variational formula. So it appeared first in as an auxiliary result in a paper of Widom in 1965, and then it was rediscovered and revived in a number of other papers, in particular in this paper by Eastgren and Karepin of 2006. And another famous paper by Marco Bertola, where he studied the dependence of isomondromic tau functions on monodromy. So the idea is basically the following. So we have this determinant, which looks like the determinant of a product of two operators. So let me write somewhere here. So we have tau of j, which is equal to the determinant on H plus of two operators P and Q, where P is equal to P plus J. So this is some operator on H plus, and Q is another operator, which is like this, P plus J minus 1. Now, the important point is that P and Q have explicit inverses. Explicit inverses which can be expressed in terms of, so if we have our jump matrix written in the form psi minus, psi plus, minus 1, and psi plus bar, psi minus, bar minus 1. So we have two factorizations, one of which is what we are looking for. So this is this psi bar is the solution of our Riemann-Hilbert problem associated to 4-point Fuchsian system. The other factorization is completely explicit. This is basically the definition of the jump matrix. And so the inverses of P and Q, they can be expressed in terms of this psi plus, psi minus, psi bar plus psi bar minus. And then in order to obtain the variational formula, so what you have to do is simply to write something like this. We differentiate the determinant of PQ with respect to a parameter, and we have here something like the log of like the trace of the inverse of P times derivative of P with respect to that parameter plus the derivative of Q times Q minus 1, the inverse here. And so this is basically what is written here. And now let us look at this formula more closely. So once again, so this psi plus, psi minus bar, they are not known, but on the other hand, we know that psi plus minus bar, they are related to phi of z, which is the solution of our 4-point Fuchsian system. So this means that these quantities, they satisfy certain linear differential equations in z variable. Now, if we use these linear differential equations to compute these derivatives here, then the evaluation of the integral basically reduces to residue calculation. And what we get in the end is some expression. So after residue calculation, we get something like trace of A naught AT over T plus trace A1 AT over T minus 1, plus some elementary correction. And so this part was precisely how we defined the logarithmic derivative of Jimbo-Miwa-Ueno tau function for P6. Okay. And so now we have identified this Widom's determinant for a specific choice of the jump matrix or the symbol matrix J of Z, a certain hypergeometric expression. So it is now identified with the solution, general solution of the isomonodromy equations equivalent to Painlevé-6. It is not, hopefully, it is not very difficult to understand that a very similar procedure can be followed in exactly the same way for a number of other Painlevé equations. So the if I come back to the to this geometric confluence diagram, so you see the important thing to have is this circle, and the circle appears when we cut so the Riemann-Hilbert problem associated to the linear system that we actually interested in. So we want to break it into two solvable pieces. So here we have two Gauss hypergeometric pieces. In the case of Painlevé-5, we will have one hypergeometric piece here and one Kummer piece corresponding to this singularity. In generic Painlevé-3, we will have two Kummer parametrices and so on. So for the most degenerate Painlevé-3, we will have two auxiliary Riemann-Hilbert problems that can be solved in terms of Bessel functions. So the point here is that for all equations from the upper part of this confluence diagram, that is for Painlevé-6, 5, and all three types of Painlevé-3, we can write the corresponding tau function as an explicit Fredholm determinant, which can already be used for efficient numerical evaluation. So given any monodromy data, you plug them into the Fredholm determinant and you get the solution of the Painlevé equation that you are interested in. For the equations Painlevé 1, 2, and 4, so the equation from the bottom part of the confluence diagram, this procedure does not work, at least naive generalization does not work, even though there was a recent work by Harini Desiraju where she managed to derive Fredholm determinant representation of the general solution to Painlevé-2 equation by basically cutting this Painlevé-2 hexagon into two Hermite auxiliary Hermite Riemann-Hilbert problems. Maybe I will say a few words on this later if there will be questions. Okay, so we have this Fredholm determinant representation, and I think that the best way to actually remember it is this graphical formula. So the tau function of a 4-point Fuchsian system. So in rank 2, so this corresponds to Painlevé 6, but actually the same is true in any rank. The problem is only that we don't know how to solve explicitly the auxiliary 3-point Riemann-Hilbert problem in the rank higher than 2. So the tau function corresponding to this 4-point Fuchsian system can be written as a product of tau functions associated to auxiliary 3-point Fuchsian systems. So this is one F2-1 parametrics. This is another one. And sorry, this is a mistake. So this is just some power of the independent variable t. This is just a constant. And then we have this Widom's determinant, which depends on these F2-1s. So auxiliary solution of the exterior 3-point Riemann-Hilbert problem and interior 3-point Riemann-Hilbert problem. So these integral operators, they are given by well, this expression, these expressions which have this integrable form. So depending on the problem you are interested in, they will be expressed in terms of Gauss or Kummer or Bessel functions. Okay, so this was the first explicit representation for general solutions of Painlevé equation that I wanted to explain. And there is another one which can be straightforwardly obtained from the Fredholm determinant. So now I will say a few words about series representation. So to derive a series representation, all what we have to do is just to expand the determinant that we have here. So this determinant of block integrable kernel, we place ourselves in the basis of Fourier modes. So instead of considering functions, vector valued functions on a circle, we now look at discrete kernel labeled by, it is convenient to label different elements of the space by half integer numbers instead of integers. And then we just make an expansion of the determinant into a sum of principal minors. Okay, so let me explain how does it go using this picture. So what is written here is basically this kernel K in the Fourier basis. Now, if we want to consider, to compute a principal minor of this determinant, so what we have to do is to choose some columns. So let's take, for example, 2 columns here. And for the minor to be principal, I have to take exactly the same rows. So we will have another row here and a row here. So then we have to restrict our huge doubly infinite in both direction matrix K. We consider this submatrix. So this is 2 by 2, okay? And the corresponding principal minor, which is a determinant of this 2 by 2 matrix. In addition, you see that it will factorize into the product of this number and this number. And this will be a general phenomenon. So if we take an arbitrary number of columns and the corresponding lines, still the corresponding principal minor will be a product of 2 factors. Right, and this is what is essentially written in this formula. So different principal minors, as you see from here, they will be labeled by well, subsets, different subsets of the set of half integer numbers. And also we should not forget that the individual elements that we have in this matrix, they are actually n by n matrices. So this means that in addition to choosing the lines, I have to choose the color of the line. So this color can be, so the color belongs to the set from 1 to n, which is the rank of our Riemann-Hilbert problem. So for the Riemann-Hilbert problem relevant to Painlevé 6, 5, and 3, so this n will be 2. So there will be lines of 2 possible colors. And so then different principal minors will be labeled by pairs, because precisely n is equal to 2, by pairs of Maya diagrams describing these finite subsets of half integer lattice. And well, with a little combinatorics, we can actually rewrite the sums over all these Maya diagrams as a double sum over Young diagrams or partitions and sum over integers. So this is the same as a double sum over Maya diagrams. Okay. Let me perhaps stress at this point that this combinatorics part is actually completely independent of isomonodromy. So whatever is the initial symbol matrix J, you will still have this expansion here. Now, what is somewhat remarkable in the isomonodromic case is that for the specific jumps that arise in that case, we can actually compute these factors, these principal minors. We can compute them completely explicitly in a factorized form. So they are given by some rational expressions of parameters. And in the end of this computation, so what we get, I formulate here the result for the most degenerate Painlevé 3 to minimize the number of parameters. So what we get is this expression for the isomonodromic tau function. So it is a sum over integers. So it is a kind of Fourier transform of a function which I denote here by B, which is itself a double sum over partitions with coefficients having explicit factorized rational form. Now, a part of this this story which I left untouched is that, well, this function b has actually a nice meaning in conformal field theory. This is how this formula was actually originally discovered. So b of sigma and t is what is called C equal to 1 central charge 1 Virasoro conformal block. But you see, we have obtained this function simply by expanding Widom's determinant into a sum of principal minors. Okay. Now, once you have this, once you have proved this series representation, it is fairly easy to implement it on a computer, say with Mathematica. So it just takes a few lines to. So this is basically. So this is our function b of sigma t, and this argument is the order up to which we want to compute this function, and this is basically the expression of the coefficients of this series that we have got by expanding Widom's determinant. So you see from here, so this is really completely factorized and really explicit expression in terms of monodromy. Okay, so you can use it to compute the asymptotics of the Painlevé function to, in principle, arbitrary order. Okay, so I think my time is almost up, so I will come to conclusions. So I have tried to explain how can we derive rigorously two types of explicit representations for general solutions of Painlevé 6, 5, and 3. So namely, we have Fredholm determinants, which I like to look at them as analogs of integral representations for hypergeometric functions. And we also have series representations. Now, one obvious question which remains is what can we do about Painlevé 6, 2, and 1? And one intriguing observation is that actually, if you just take a few first terms in the asymptotic series of the corresponding tau functions, you will have exactly this periodic structure which emerges, except that now we don't know how to compute the analog of the function b in some other way, not using the differential equation directly. So conformal block interpretation is also missing in this irregular case. Now, there is a recent progress. So this paper by Harini Desiraju that I have already mentioned, and there is also another very interesting work where this periodic structure emerges. So this is the paper of Ivaki, where he constructs this general solution of P1 using topological recursion. There is a lot of activity on Q Painlevé version of this story by Bernstein, Shochkin, Gavrilenko, Marshakov, Jimbo, Nagoya, Sakai, and other people. And one more thing that I like to mention perhaps because this is relevant to the present meeting is that one can use this explicit representation for Painlevé functions to study spectral quantum mechanical problems like for Hoyne equation and Mathieu and cubic and quartic oscillator. So there was also a lot of activity in this area starting from maybe 2015 and up to now. Yeah. So that's all that I wanted to say. So thank you very much for your attention.
Oleg, are there any questions?
Yes, please.
Yes.
I'm interested from my own private perspective on the hypergeometric content of what you're doing. When I work with my collaborators, we progress through the normal list of hypergeometric functions and Hoyne functions. And then my collaborators get very happy when they can finally reduce something to a Maya G hypergeometric series, which is sort of kind of saying, at this point, we give up and just call it Maya G. Do you get as far as that? And do you get further than that?
I'm not sure I understood the question. So if, are you talking about higher rank generalization?
I'm just talking about I mean, you've mentioned hypergeometric series, comma series, yes. Mm-hmm. Hoyne functions, which are hypergeometric series. When you push this as far as you go, what's the limit of hypergeometric complexity which you encounter? Do you need Maya G functions?
Well, actually, for me, Hoyne is not hypergeometric. Okay, so when I'm talking, first of all, when I'm talking about hypergeometric, I can have in mind only two generalization or extensions of F21. So basically, I can go in one direction, having F11, which is Kummer, F01, which is Bessel, and then Airy and Hermite functions I would also call hypergeometric. On the other hand, if we study, for example, these Fuchsian systems, but in higher rank, and you try to put some restrictions in such a way that the problem remains solvable, because you see in this formula for the tau function, so the building blocks are solutions of this auxiliary 3-point Fuchsian systems. So these solutions can be constructed in higher rank when we study hypergeometric, when we use hypergeometric functions like f n-1. So this Thomas, Clausen-Thomas hypergeometric functions. But then again, here you can make a degeneration similar to this one. So of course, you will get n-1, n-1, and so on. Okay, so all of these cases fit into the scheme, of course.
Thank you, that's very helpful.
Are there any other questions? If not, it just remains to thank Oleg for this nice talk, and we'll resume again in 10 minutes' time.